So just because I looked at 3 papers and already saw 2 mistakes. It looks like this if you freeze frame it at any moment. Okay. Draw a free body diagram representing the system. Then I'd say overlay a coordinate system on top of that system. On top of your free body diagram to help isolate the forces and deal with the fact that this is an unbalanced system. Take any off-axis components or forces and break them into their components. Maybe write a Newton's second law and Newton's first law relationship because I don't want T in my answer. So net force in the x direction equals MAC. So that looks to be T sine theta equals M V squared over R. And T cosine theta equals mg. Any question about where any of that came from? Again, first semester physics. I got an R in there I'm going to have to deal with in a bit, but we'll let it ride for now. If I divide these two, I'll get tan theta equals V squared over RG. We still good? All right. That means V is going to be square root of RG tan theta. This is just temporary though, because I'm not really interested in V. What did I ask you to find? The period. That's right. Not this T. This is what? Tension. I want the period. I don't need my free body diagram anymore. I have an object traveling in a circle. And I know that the velocity of an object traveling in a circle, if it's a constant, it's just going to be the circumference divided by the time it takes. And so the period is going to be 2 pi r divided by v, which is going to be the square root of rg tan theta. This is kind of a mess, and I'm not seeing it being easy, but I'm going to go ahead and I'm going to leave the 2 pi out because 2 pi shows up in almost every one of these things where something's traveling in a circle. But in the radical, I'll have r over g tan theta. When I put it all under the radical, I did r squared on the top, and I canceled the 1 r on the bottom. But I didn't say we could have r in our answer, but I will say you can have L in your answer. So there's a relationship between r and L. R is going to be L sine theta. So I want to introduce L in here. Remember, we're trying to compare this to a pendulum. So let's introduce that. Here's where it's going to get a little messy. Top's going to be L sine theta. And the bottom is G tan theta. But tan is sine over cosine, right? So if I do that substitution and put my sine over cosine here, it looks like the sines cancel out, and I'm left with cosine. You guys see that all right? So one more step over here, and I'll have t equals 2 pi times the square root of L cosine theta divided by g. Now, somebody asked, can we use the small angle approximation? Sure. But this isn't sine. This is cosine. We did keep the angle small though, right? Why don't you just take a quick journey with me. Cosine of 1 degree is a 0.9998. Say cosine of 3 degrees. 0.999. Cosine of 5 degrees. 0.996. If I was to come up with a small angle approximation for cosine, what do you think it is? 1. Yeah. So if I keep my angle small, cosine theta is nearly equal to 1. If I do that, I get that the period of something traveling in a circular path that's hanging on a string is the same as the period of a pendulum, applying the same kind of rules to our pendulum as we do to our object traveling in a circle. Now, when we did this first semester, we left the cosine in there because I gave you an angle. But in this case, we're trying to see the similarities between circular motion and simple harmonic motion. Just showing you that the pendulum and the circle have the same period, that's just one data point. You guys, especially you guys in pre-calc, have had the luxury of studying the unit circle. I know how much you love studying the unit circle. I hear about it almost all the time. You guys love it almost as much as you love studying physics. So it's good to know studying the unit circle is still one of your favorites, just like physics. So here we go, the unit circle. And I hope none of you find it triggering, but let's consider this point right here. Okay, this point is something that you guys know you can define based on knowing, say, r and theta. How would I define that point? What's the x and y coordinates of that point? Go ahead. No. If I want to find where that point is, I'd probably have to use some trig functions in here. Go ahead. R cosine theta for x and r sine theta for y. True enough? You guys do all remember that? Well, we're talking about things that are moving in this class, right? So what if instead it's not just a spot that that's at rest, but a spot that's going in the circle? Okay, so it's traveling around in a circle. That doesn't change. The fact that it's going in a circle doesn't change that its x coordinate and y coordinate are still based on theta, but theta keeps changing. Do you have any relationships that you might know that talk about how theta might change with respect to time for something that's going around in a circle? That's too bad, because I gave you one. Theta equals 1/2 alpha t squared plus omega times t. Right? Now, the little dot that I was making go around in the circle, I'm not accelerating it. I mean, it has a centripetal acceleration, but does it have an angular acceleration, or is it traveling at a constant speed? Constant speed, which suggests that the acceleration is 0. That would mean theta, for an object traveling in a circular path, would have an expression that would just be omega times t for something that's just traveling in a circle. That would change out my expressions for x and y to be expressions that would have omega t in them, where omega represents the angular speed of the object. But you recognize this, right? Doesn't this look like our function for an object traveling in a circular path? Doesn't it also look like our object traveling in simple harmonic motion? Isn't this the expression we use for an object traveling in circular motion? Except that instead of r, we have x naught. It should look familiar, because simple harmonic motion is just a projection of an object traveling in circular motion. So if you look at it from the side, like the video we just watched, It's not just fake simple harmonic motion, it is actual simple harmonic motion. This is still the same solution that you get from a second order differential equation, where omega in this case is the actual angular speed in radians per second, as opposed to a construct related to something like the spring force and the object's mass. So omega is a real thing that deals with how something travels, whether it's in circular motion or simple harmonic motion. And they are the same thing. It's just that you're looking at one dimension of something traveling in circular motion. In fact, to kind of demonstrate that, I would like you to solve for something, and I found in first period couldn't do it. But maybe you guys will be better because, more awake and all that stuff, right? Can you tell me, and I need you to show this, it only takes a couple of steps, but maybe you'll have to. Can you show me how long it would take for an object to travel in an orbit near the surface of the Earth? We did this not long ago for practice. Assume the object traveling in circular motion has a mass of, say, ms. Let's say that this is the Earth and you're very close to the surface, so we'll say re for the radius of the Earth, and we'll say the Earth has a mass of me. I'm just looking for the period of a satellite traveling in a circular orbit near the surface of the Earth. Nice to see a variety of things are going on. I would have started with net force equals MAC, and then recognize that this is from gravity, so ME ms g over RE squared, which has to equal ms v squared over RE. So we solve this for v, you can get the square root of me g over RE. We've done this a bunch, so I don't feel too horrible about expecting it from you. Now, this isn't where we end, though. To find the period, I want you to realize that the velocity equals 2 pi r over t, where this r is the radius of the Earth, and that v is the velocity to be in orbit. So the period equals 2 pi times the root of RE cubed over MEG. Just substitution. And take that R, square it, put it in a radical. I jumped a couple of algebra steps. If you need to see them, you should probably say something. So factor out the 2 pi RE and multiply by V, but the inverse of V, because it's going to be in the denominator. So that's going to be the root of RE over MEG. And then take the RE and square it. So you can combine it with the other RE. And RE squared times RE is going to be RE cubed. That all right? That's all right. No worries. No problem? First semester. So I do have to expect you guys to be able to do things. But today, I want to kind of talk about something that's a little bit weird. It's a phenomenon. It's something that's in every physics book. So just hold on to this for a few minutes, maybe tuck it away, and consider this case. What if we could, instead of going around the Earth, go through the Earth? Like physically drill a hole right through the center of the Earth. There we go. A hole through the center of the Earth. Make it a little wider so we all fit. There we go. Now, if you were to take, say, one of you and drop you in the top of this hole, it's not a secret that at this moment you would feel a force pulling you downwards, correct? And so you would begin to descend through the planet, through the hole. Eventually you'd make it say partway through. And is it clear to you that at this moment the force on you would be less than it was near the surface? Are we sure we're okay with that? Just for a few of you, just to make sure, imagine it. A simple way to imagine it is to consider that if we divided up the Earth into two parts, do you see how there's less mass above you than below you? So the force downward would be greater than the force upwards, but it would still be less than it was when you were sitting at the surface when all of the mass of the Earth was below you. So the force is getting smaller. In fact, eventually, you would make it to, say, the middle, where there's equal amounts of Earth all around you. And what would the force be there? 0. So we are seeing a force that's getting smaller as we get towards the center, or you could say a force that's getting bigger as we get away from the center. And we already know that for things that are in harmonic motion, there has to be this opportunity for the force to be getting smaller, go to 0, so there's an equilibrium position, and then get bigger as you get away from the equilibrium position. Because when you make it here, it's not like you're just going to stop, right? You've been spending all this time falling towards the center of the Earth, and now you've got some velocity and momentum behind you, so you'll keep going until you pop out the other side. And if somebody's there to grab you, great. If somebody's not, or they miss, or they don't like you, then they just let you fall back in, and this whole thing repeats. You pop out the other side. I think this would be harmonic motion. The question is, would it be simple harmonic motion? And to be simple harmonic motion, it has to fit the differential equation. This case I'm going to use r, because that's going to be the variable I'm going to use for how far away we are from the origin. That has to equal minus sign a constant times r. Right? Differential equation. So let's try it. See if we can figure out how this would work. To do this, we need to figure out what the size of the force is in terms of r. Like, let's say we are somewhere here, some distance away from the center, a distance r. Because we know what the force would be at the surface of the Earth. We just did that problem, so we have an idea of what that force looks like. That's going to be me times the mass of u times g divided by r squared. That's the force at the surface. I'm interested in the force if you're right there. Now, this is the part that's hard. Of all the things I've talked about today, this is the part that you'll have to buy into. And if you don't want to buy into it, then you're not going to get it. And that's okay. But like I said, this is kind of a thought experiment. It's not like we can actually drill this hole. So let's consider the thought experiment for a moment. Now, is it true, or you understood the whole point that at this moment there's more Earth below you than there is above you? That part's okay, but it's really hard to figure out the force upwards because this is a portion of a circle, a portion of a sphere actually. That would be difficult to figure out how much mass is above you. And remember, the force of gravity is based on how far each piece of mass is. That's going to be a complicated bit of calculus. But there is a way to do it without doing calculus at all. And it has to do with considering this shell. What I mean by that is, right now where we are, if you look, there's a hold on. That R defines a sphere of the Earth, right? I just drew a circle there, but that represents a sphere, like a part of the Earth that's still underneath us. And then there's a shell of Earth around us. Like, I could put this back in place and we realize, if we only were considering the shell of Earth around us, there's all this shell all around us. You guys see that kind of idea? If you're inside here, say right here at the middle, it's easy to believe that the net force on you would be 0 because you're right at the very middle and you have equal amounts of mass all around. But believe it or not, it can be shown that even if you are over here, the net force on you would be 0. if you're inside a symmetrical spherical shell. I can't prove that to you. In fact, I'm not going to try, because that does involve actually a lot of calculus. And you have to say, well, how much does this chunk of Earth affect me? And then add that up for every chunk of Earth in this spherical shell. That's a difficult calculation because you're different distances from every piece. And so the math on that's pretty challenging. But you would buy it if we were at the very center. So again, I'll make the quick argument that if you could just take the Earth and divide it up like that, you have less Earth, to the upper portion of you, but it's closer to you, and more Earth in the bottom right portion of you, but it's further away. And due to the fact that it's a sphere, the symmetry causes that force to cancel out. So if you could make a chamber in the center of the Earth, you would find that if you were in that chamber, you'd be able to float around in it. But of course, I've seen King Kong and Godzilla. We know that King Kong lives there, and Godzilla lives on the outside, and the two aren't supposed to meet because Godzilla has to be king of all the monsters. And if King Kong is a Titan and comes out, Godzilla's got to fight him. It's a whole big thing. They have beef. They beat each other up. But Godzilla, he'd rather be down there until he found out that there were other, ape-like things down there. And then it was a whole thing because they had another Titan that was kept. These movies are just difficult to watch. But you should know there is an entire group of people who believe in the hollow Earth theory, that the Earth is hollow, and that there is a species of people who live down there, and that NASA's been hiding the evidence for years because they have satellite images of the hole that exists in the Arctic where people enter to get to this particular hollow Earth portion of the Earth. It's fake. There's nothing in the center of the Earth but molten iron. But let's just assume that movies love to glamorize this. The truth is, the only part of the Earth that actually contributes to the force on you is the part of the Earth that is inside this circle. The shell doesn't. So if I wanted to consider the size of the force on you, that would be a gravitational force that would be the mass of you times the mass of the, I don't know how you want to put this, the pit of the Earth, right? It's like the pit inside there, times g divided by r squared. So we have to figure out what the mass of this pit is. So we're talking about trying to figure out how much mass of Earth is here. That sounds hard to do until you realize we could consider that the mass of that pit would be proportional to the volume of that pit, which has to equal the mass of the entire Earth divided by the volume of the entire Earth. Right? You know about density, don't you? That's how density works. So if we assume the Earth has a uniform density, it doesn't, but let's say it does, it'll be fun. Then this ratio has to be true. Well, the mass of the pit divided by the volume of that pit, that volume would be 4/3 pi little r cubed. Compared to the mass of the Earth and the entire volume of the Earth, which would be 4/3 pi capital R cubed. All good? So cancel out those 4/3, solve for the mass of the pit, and we get mass of the Earth times little r cubed divided by big R cubed. Everything okay? All right. I'm out of space a little bit, so I'm just going to kind of take this and substitute in for the mass of the pit. All right? So we'll do that over here. I'll get net force equals mass of U times G times mass of Earth times R cubed over big R cubed. But don't forget there is that R squared there. All right, so I'm taking this and replacing the mass of the pit with this. All okay? A little bit of math there. I will say, too, that if R is positive, then this force is negative. Right? It's pulling down. We are a positive distance away from the center. So the force is in the negative direction. Everybody okay with that too? All right. This has to equal the mass of u times, well, the acceleration. So if I just collect some terms over on the other side and make it a little cleaner, I'll get minus the mass of u times the mass of the Earth times g over the radius of the Earth cubed times r. Now I'm going to cancel out the mass of u because obviously that doesn't need to be there. And I'm going to replace a with d squared r over dt squared, which equals minus, and let's see, I have a collection of constants times r. Right, this is a second order differential equals a minus sign times a collection of constants times a displacement. That is the expression for a simple harmonic oscillator, which means the period of these oscillations has to be equal to 2 pi divided by omega. Well, based on what we know, omega has to be the square root of MEG over RE cubed. So 2 pi times the square root of RE cubed over MEG. Does it look similar to something else we've seen today? I mean, I just have to kind of pan over here, right? So whether you go in a circle around the Earth or you drill a hole and fall through the Earth, it takes the same amount of time to do so. Interestingly enough, I can't convince you of this, and I won't even try, but you don't have to drill that hole through the center. If you drill that hole here, say here, you'll find the exact same value because the force is less because you're going at an angle. And if you use the sine function, you find it eventually cancels out, and you get the exact same period, which means if you drill a hole between any 2 points on the planet, the time it takes to get there would be the time it takes to do half an orbit, or a round trip would be an entire orbit, which we did already earlier in the year.